Hello ma'am. My first question is that what is cogeneration system? Second question is that how the system efficiency is getting improved with this cogeneration. And third question, please solve one problem with cogeneration system and without cogeneration system with the help of the Moliere diagram and steam table. Let us understand cogeneration system with the help of diagram. What is the meaning of cogeneration? So it is the sequential generation of two useful forms of energy from a single primary energy source. Now we will understand the working of cogeneration system with the help of diagram. We know that in boiler, steam is generated at high pressure and high temperature. Now this steam is provided to the turbine and the enthalpy of this steam we will refer here as a point 1. That is the enthalpy H1 is there for the steam entering to the turbine and it is at high temperature and high pressure. Now in turbine, isentropic expansion process is taking place. That means the expansion is having entropy constant. So here after the isentropic expansion, the mechanical energy is used to generate the electricity in this generator. So here the first form of useful energy, that is the mechanical energy, is getting converted into electrical energy. Now the remaining steam at low pressure and low temperature is again provided to the process plant. So here this steam is having heat energy. So this is the second type of useful energy in the form of heat is provided to the process plant. So at this point 2, that is at the outlet of the turbine, at point 2, enthalpy of the steam as well as water mixture is provided to the process plant and the whole steam is getting converted into saturated water. So enthalpy before entering to the turbine, that is H1, then here enthalpy at the outlet of turbine, that is H2, and this steam as well as water mixture is converted into saturated water. So enthalpy at the exit point of process plant will be HF2. So I will write here, this point is at H1, here is H2 and here is HF2. Now again this saturated water is pumped to the boiler. So this is all about the working of cogeneration system. Now the second question is that how the efficiency is getting improved with the help of this cogeneration system. So for that we will solve one problem. We will find out the overall efficiency for the system with cogeneration and system without cogeneration, and then we will compare the overall efficiency for these two systems and we will find out how the efficiency is getting improved with the help of cogeneration system. So first I will read what is the given problem. A process plant heating load is 8.5 megawatt. It is supplied by a back pressure turbine whose exhaust pressure is 2 bar. The condition of the steam entering the turbine is 25 bar and 50 degrees Celsius superheat. The isentropic efficiency of the turbine is 0.8 and generator efficiency is equal to 0.95. Assuming the saturated condensate coming out of process plant is fed to the boiler. Assuming the boiler efficiency is 0.85, find out the power developed by the system and overall efficiency of the whole plant. If the power calculated in the previous system is developed in turbine with the same inlet condition and exhaust pressure is 0.1 bar and the required heat load is supplied by the another boiler where steam is generated at 2 bar and saturated. The condensate from the both system is fed to the boiler. In this case, find out the overall efficiency considering both systems together. In this case also turbine neta, boiler neta, that is the turbine efficiency, boiler efficiency and generator efficiency in case B are same as in case A. So this was the given question. Let us first understand given data with the help of diagram. It is given that the process plant heating load, that is 8.5 megawatt. So we will write here the heating load is 8.5 megawatt for the process plant. Turbine exhaust pressure. So this exhaust pressure at turbine, it is given 2 bar. So we will write here the pressure is at 2 bar. Then steam entering turbine. So here from the boiler, steam is entering towards the turbine and it is at 25 bar and 50 degree Celsius. Then efficiency of the turbine is given, that is neta turbine is 0.8. So I will write here neta T is equal to 0.8. Then the efficiency of generator is also given, it is 0.95. So we will write here neta G is equal to 0.95. And efficiency of the boiler is also given, so I will write here as a neta B. So neta B is equal to 0.85. So this is the given information for the cogeneration system, and for this we have to find out what is the power developed and what is the overall efficiency. Let us first find out the different values of enthalpies with the help of the steam table and Moliere diagram. Now if we observe what is the condition given for the temperature of steam at inlet of the turbine. So this temperature of the steam is given that it is at 50 degrees Celsius and superheated state. So first we will find out what is the superheated temperature of the steam at the entrance of the turbine. So we have to find out the temperature of steam at 25 bar and we have to add this 50 degree Celsius. So for that we will use here the steam table. So from the steam table we will find out the temperature at 25 bar. So pressure is given, so we have to refer here the pressure table, that is the saturated water and steam pressure table is there. Now at 25 bar pressure we will find out what is the temperature. So here it is given that in the first column pressure is given 25 bar and in second column temperature is given and it is 224 degrees Celsius. So this 224 degrees Celsius plus already 50 degrees Celsius and superheated state is given. So we have to add this 50 degrees Celsius, so which is equal to 274 degrees Celsius. So we can say that the superheated state, that means the temperature is 274 degrees Celsius, steam is entering the turbine. Now we will find out what is the HF2 at 2 bar pressure. Now if we observe at the exit of the turbine, pressure is maintained is 2 bar, and this 2 bar pressure steam and water mixture is entered into this process plant, and here all this mixture is getting converted into the saturated water, and here enthalpy of this saturated water that we have to find out. So for saturated water, that means the fluid is in the liquid form, and that's why we have to take here suffix as a F. And from the point 2, this mixture is getting converted, so we will say here as a HF2. So pressure remains same, that is the 2 bar. So we have to find out the value of HF from the 2 bar pressure. So for that we will again refer the pressure table, and from this pressure table we have to take the 2 bar pressure. So here this 2 bar pressure is given and value of HF, that is 507.4 kilojoule per kilogram. So we will write this value, that is the value of HF2. Now we will find out what is the enthalpy at this point 1 as well as enthalpy at this point 2. So how to find out? So here enthalpy at this point 2, we have to take the condition of steam. So it is at 25 bar and temperature is 274 degrees Celsius. So from this temperature we will select, from this data pressure and temperature we will select the point 1 on the Moliere diagram. And then in turbine isentropic expansion is taking place, and therefore we will take the vertical line at constant entropy. and then we have to extend this line at constant entropy up to a pressure of 2 bar, and we will select the point 2, and from that we will find out the value of H2. This is the Moliere diagram and also known as enthalpy entropy diagram. Now we will select the point 1 and point 2 as per given condition. Now initial condition is given pressure 25 bar and temperature 274 degrees Celsius. Now as per the given data we will select the point 1. So I will enlarge this diagram. Now if we observe pressure is given here, that is 1 bar, 2 bar, 4 bar, 10 bar and so on. So these are the pressure lines. If we observe in between 20 and 50 there are two lines. So this line is for 30 bar and this line is for 40 bar. So in between this 20 and 30 we have to select the 25 bar pressure, and temperature is also given, and temperature is 274 degrees Celsius. So here 300 degrees Celsius, 350, 400, 450 and so on. So these are the temperatures given. So we have to select the line for these are the pressure line. So in between this 20 and 30 we will select these middle points are for 25 bar pressure line, and temperature is 274, that is below 300 degrees Celsius. Here is the exact temperature 274 degrees Celsius. So this is the point 1. Now how to measure the enthalpy at point 1? So for that we have to draw here one horizontal line. So we will select here one line and we will mark one horizontal line to find out the enthalpy. Now if we observe this enthalpy is below this 3000 and exact value is 2950 kilojoule per kilogram. Now we will move to select the second point. So here the isentropic expansion process is taking place in the turbine. So we have to first select the point 2. So here entropy remains constant from point 1 to the point 2 and pressure is 2 bar. So if we observe here is the pressure, that is 2 bar. So we have to draw one vertical line passing through this point 1 and for a pressure up to 2 bar. So I will select here one line and we will draw one vertical line that will be passing through this point 1 and for a pressure up to this 2 bar. So here is the point. So that is the point of intersection. So this point will be 2 dash. So how to measure the enthalpy at this point 2 dash? So again we will draw here one horizontal line passing through this point. So we will select here the line. Now this point will be the point 2 dash. So again we will draw here one horizontal line and it is below 2500. So it is exact value, that is H2 dash is equal to 2480 kilojoule per kilogram. Now we have to note down this H1 as well as H2. Now isentropic efficiency is given, that is 0.8. So with this isentropic efficiency, how to find out the value of H2? So for that we have the formula, that is H1 minus H2 dash multiplied by isentropic efficiency is equal to H1 minus H2. So we will put the value of H1 and H2 dash. Now only one unknown value, that is H2, and H2 is equal to 2574 kilojoule per kilogram. Now we will find out the mass of steam supplied. For that, if we observe the given data, then here it is given that the heat given in process plant, that is equal to 8.5 megawatt. So how we can define this heat? So heat provided to the process plant, that is equal to this amount of mass of steam supplied multiplied by the enthalpy difference. Now enthalpy difference in this process plant is here, enthalpy is H2 at the entrance of process plant, and here at exit it is HF2. So we have to take this enthalpy difference, that is H2 minus HF2. So amount of heat supplied 8.5 megawatt. So standard unit is kilowatt. So 8.5 into 10 raised to 3, which is equal to ms, and H2 minus HF2, that is 2574 minus 504.7. So ms is equal to 4.1 kilogram per second. So this is the amount of mass of steam supplied. Now we will calculate what is the power developed by generator. Now if we observe, here is the generator, and this mechanical work is getting converted into electricity in this generator, and this generator is having efficiency 0.95. Now if we observe how to find out the power developed by generator, then we have formula, that is the mass of steam supplied ms and enthalpy difference in the turbine multiplied by this efficiency of the generator. So enthalpy difference in turbine at the entrance, enthalpy at point 1, that is H1, and here at the exit enthalpy at point 2, that is H2. So we will put here the value, that is 4.1 into 2950 minus 2574 into 0.95. So power developed by generator is 1464.5 kilowatt. Now we will find out what is the total heat supplied to the boiler. So the heat supplied to the boiler with efficiency neta B is given 0.85. So heat supplied to the boiler QB is equal to this amount of steam supplied ms in the bracket enthalpy difference. Now if we observe at the entrance, what is the enthalpy at the entrance of the boiler? So this is HF2. So this is the enthalpy of the steam, and at the exit of the boiler the enthalpy is nothing but this H1. So this HF2 and H1, we have to take the enthalpy difference, and we have to divide it with this efficiency of the boiler. So we will put the value ms 4.1, H1 2950 minus 504.7 divided by 0.85. So answer is 11,795 kilojoule per second. So this is the amount of heat supplied to the boiler. Now how to calculate the overall efficiency? So efficiency is nothing but output by input. So output of this whole system is in the two forms of energy. One form is the power output from this generator, and the second form is the heat supplied to the process plant. So output, we have to add power from this generator that we have already calculated, plus heat supplied to the process plant, that is given in the data 8.5 megawatt, divided by input. So what is the input? So input is nothing but the heat supplied to the boiler. Now we will calculate this. So here heat given, that is overall efficiency output from turbine. So output from turbine, that is nothing but here the power developed by the generator, that is 1464.5, plus heat given to process plant, that is standard unit is kilowatt, so 8.5 into 10 raised to 3 divided by total heat supplied to the system, that is heat supplied to the boiler. So it is given that 11,795. So when we calculate this, we will get 0.845, that is 84.5%. So this is the overall efficiency of the cogeneration system. Now we will calculate the overall efficiency for this system without cogeneration. That means the first form of energy, that is in the form of electrical energy, steam is supplied from the boiler 1, and the second form of energy, that is the heat energy for the process plant, the steam is supplied from the boiler 2. Now if we observe the first system, so as per the given data, here at the inlet of this turbine, it is at 25 bar pressure and 50 degrees Celsius, and steam is in the superheated form. So we have to take the superheated temperature, that is 274 degrees Celsius, and pressure is 25 bar, and we will find out the enthalpy at point 1. Now we have to find out the enthalpy at the exit of the turbine. So here for this system, the pressure is given 0.1 bar. So the process is isentropic, that means entropy remains constant. So at this point 2 or at the exit of the turbine, we will calculate the enthalpy H2. We will also consider the efficiency, that is neta turbine efficiency 0.8, that is given, and we will consider this and we will calculate this H2. Now again after that there is the condenser, and after at the exit point of condenser there is the enthalpy, that is the saturated water is coming out from the condenser, so we will find out the enthalpy HF2. So here pressure remains same, that is 0.1 bar. So from steam table we will find out from the pressure table what is the value of HF2. So here in the first column there is the pressure given and we will find out the 0.1 pressure. So here is the 0.1 pressure and value of HF is 191.8 kilojoule per kilogram. So we will write this. Then we will move for the second, that is for the second form of energy, that is the heat energy. If we observe the given conditions, here is the 2 bar pressure line. So this 2 bar pressure, steam is coming out of the boiler. So here is the fluid, that is what is the phase of this fluid, that is in the gaseous form, so we will say steam. And in the process plant, heat is getting provided, that is 8.5 megawatt, and it is coming out as a saturated water. So here pressure remains same at the inlet of process plant and at the outlet of process plant. So we will calculate this point, we will say this is the point 2, that is H2 at the process inlet of the process plant. So this is in the form of steam. So how to find out the enthalpy at 2 bar? So again we will use here the pressure table and we will find out the pressure at this 2 bar. So here is the 2 bar pressure and here this is in the gaseous phase. So enthalpy we will say Hg. So Hg is 2706.3 kilojoule per kilogram. Now at the outlet of process plant, it is in the saturated water condition, and this is also mentioned in the question. So saturated water, that means we have to refer here as a HF. So this HF we will consider here as a HF2. So I will write here at the inlet we will consider the enthalpy H2 and here we will consider as a HF2. So this HF2 for saturated water, that is HF value at 2 bar is 504.7 kilojoule per kilogram. So we have to write all these values from the steam table. Now how to find out this value of H1 and H2? So for that we will use the Moliere diagram. Now we will select the point 1 as per the given condition, that is for 25 bar and 274 degrees Celsius. So here is the point 1 that we have already selected, and H1, that is the enthalpy related to this point 1, that is 2950 kilojoule per kilogram. Now final condition is given 0.1 bar and efficiency, that is the expansion process in turbine that is taking place, that is isentropic expansion. Now on this horizontal line entropy is given, so this entropy remains constant. So we have to draw one vertical line passing through this point 1 and we have to extend this up to a pressure of 0.1 bar. Now if we observe, here is the pressure, that is 0.1. So we have to extend this up to 0.1 pressure bar. So we will select here the line and we will draw straight vertical line passing through this point. And we have to extend this point up to a pressure of 0.1 bar. So here is the point that we have selected. Now how to find out the enthalpy at this point? So for that we will again draw one horizontal line passing through this selected point. So this point will be 2 dash. Now this isentropic, if expansion is taking place, so this point will be 2 dash. Now to find out enthalpy, we will draw here one horizontal line. So this is the horizontal line. Now if we observe here, we will draw here the correct horizontal line. that is here is the point of intersection. So how to find out the enthalpy? So if we measure this scale, here is the one part, second part, third part, fourth part and fifth part. So total 5 parts are there in between 2000 and 2500. So we will measure this, that is H2 dash. So enthalpy at this point 2 dash is known as H2 dash and it is equal to 2181 kilojoule per kilogram. Now how to find out the exact value at this point 2, because here the isentropic efficiency is given 0.8. So we will use here the formula, that is H1 minus H2 dash multiplied by 0.8, which is equal to H1 minus H2. So here value of H1 is known, then value of H2 dash is also known. So H2 dash value is at the pressure of 0.1 bar. And then we will find out the value of H2. So H2 is 2335 kilojoule per kilogram. Now we will calculate the amount of steam supplied to this power plant as well as this process plant. Now how to calculate? So for this, first we will take the amount of heat supplied, that is equal to power developed divided by the enthalpy difference. So power developed in this generator and that we have already calculated, and divided by enthalpy difference, that is enthalpy at point 1 and enthalpy at point 2. So we will take P divided by H1 minus H2, 1464.5 divided by 2950 minus 2335. So which is equal to 2.38 kilogram per second. So this is the amount of steam supplied to this system. So this is the first case, or we can say that the first form of energy. So we will use here the suffix 1, that is ms1. Now we will move for the second form of energy, that is the heat form in this process plant. So again we will calculate what is the amount of steam supplied and we will use here the suffix 2. ms2 is equal to amount of heat supplied, that is 8.5 megawatt. So we will take this into kilowatt, 8.5 into 10 raised to 3 divided by enthalpy difference. So enthalpy difference is H2 and this HF2 at the entrance and exit. So we will take H2 minus HF2 and we will take here the answer 3.86 kilogram per second. Now we will find out the total energy output from both the systems. So from this system first, here is the power output in the form of electrical energy. So this power output that we have already calculated, it is 1464.5. And in the second system, here is the energy in the form of heat and it is provided 8.5 megawatt. So we will take the standard unit 8.5 into 10 raised to 3. So if we add this, then we will get the total energy 9965 kilojoule per second. Now we will move for the energy supplied to both systems. So how much energy supplied to the boiler 1 as well as boiler 2. So for that we will observe here, we have to take this amount of steam supplied multiplied by the enthalpy difference. Now if we observe here, for the first system, what is the amount of steam supplied, that is ms1. So we have to use here suffix 1 and that we have already calculated. And enthalpy difference, so at the entrance enthalpy is HF2, that will come from the condenser, and at the exit enthalpy will be H1. Now this H1 and HF2, if we observe H1 that we have to take at 274 degrees Celsius and 25 bar, that we have already taken, and HF2 that we have to take at 0.1 bar pressure. So we have to take these both values plus, now for the second system, how much amount of heat energy supplied to the boiler second. So again amount of steam supplied multiplied by the enthalpy difference. So amount of steam supplied ms2 that we have already calculated, and enthalpy difference, so here is H2, enthalpy at the exit, and at the entrance it is HF2. So this H2 and HF2 we have to take at the 2 bar pressure and that we have already taken, so we have to put the values. So when we calculate this, we will get here the 14,550 kilojoule per second. Now how to calculate the overall efficiency? That is, efficiency is equal to output by input. So this output is 9965 and input is 14550. So this ratio is 0.685 and that is equal to overall efficiency 68.5%. Now if we compare the overall efficiency with cogeneration and without cogeneration. So with cogeneration it is 84.5% and without cogeneration it is 68.5%. So from this we can say that the system efficiency or overall efficiency is getting improved with the help of the cogeneration system.